Hey everyone, this is the first video in a series of 3 for the Project 5 walkthrough, which is our machine learning project. I'm going to do a little bit of an overview of Project 5, and then I'm going to be specifically talking about BinarySearchTree.h. We're going to spend time going through the actual file, the source code that you're given, and I'm going to go over each specific function that you'll be implementing and spending a little bit more time and detail on the trickier functions. Just to note that this slide deck and presentation is supplementary information for Project 5, and your primary source of info should still be coming from the project spec. So please do be reading that and referring back to that. You will need it to complete the project. So ultimately, the goal of Project 5 is that we're going to be creating a program that is able to classify Piazza posts and predict a label for them based on the information that we have trained it on previously. We're going to start with BinarySearchTree.h. The next video in the series will be map.h from Ashley. Then Andrew will finish up with the main.cpp, or our driver program. And map.h builds off of this binary search tree that you'll be implementing. Main does not use our version of map. It's going to use the standard map from the STL. So in BinarySearchTree.h, you will be implementing the following functions. They are private helper functions for the binary search tree class. We will be going in depth for all of these, or we'll be looking at all of these in the actual source code soon. But just to give you an idea, these are all the functions that you'll be implementing. Just to talk a little bit about a binary search tree, your binary search tree will not have to handle duplicates, so you do not have to worry about ever inserting a duplicate element into your binary search tree. It's important also, the whole part of being a binary search tree is that it has a sorting invariant that must be maintained. A pointer to a node is either a null pointer, or everything directly to the left of it must be less than the current node, and everything directly to the right of it must be greater than the current node. And it's not just that the left is less than and the right is greater than, but the entire left subtree is less than the datum that you're currently looking at, and the entire right subtree of a datum that you're currently looking at must be greater. So that's the sorting invariant of our binary search tree. Everything to the left, less than, everything to the right, greater than what we're currently looking at. And that's going to come into use for us, especially when we're looking at the check sorting invariant function. So note that what is defined as less than or greater than are going to be specific to the type of element that's in your tree. So we have a custom comparator that's taken in. It's default set to standard less if no argument is provided. But this does allow for more flexibility and allows us to adapt the binary search tree to sort it with a map, which contains elements that are pairs rather than individual primitives. So our solutions are going to be recursive. A common structure is that you'll have a base case of when you have an empty tree or when a node is equal to a null pointer. And then often you will be calling on the left and the right children to do some sort of operation or find out some information about the binary search tree. But there is quite a bit of variation in these functions, and the recursion can be tricky sometimes. So it can take some careful thinking to figure out all of these different functions. Also, our binary search tree is going to be using the big three. That's because these nodes are dynamically allocated on the heap. So every time, or we need to overload the big three, the copy constructor, assignment operator, and our destructor, so that when, if two trees are set equal to each other, they're creating their own deep copies, and also they're being properly destroyed when they go out of scope. So now we're going to take a look at the actual source file, BinarySearchTree.h. We're going to go through it, talk about functions, and also be doing some diagrams for the trickier functions. Okay. Oh, wait. Oopsies. I think I need to reshare my screen. Okay, so we're now looking in VS Code at BinarySearchTree.h. This is the starter file. So this is what looked out fresh out of the box if you download the starter file. So we're going to go through this together, help break it down a little bit. So we first have our node struct here, and that's just what each node is going to hold in our tree. We can see that it's related with left and right pointers like it should be. We also see the starting of the implementation of the big three, and you will be implementing the copy nodes impl and the destroy nodes impl that are used in these copy constructor, assignment operator, and destructor. And then if you've taken a look at this file before, you'll notice that for every function that we're implementing, we are implementing the functions that end in impl, but there's also a version that doesn't have that. And so you might be thinking, why do we have this? And then we also have the impl version. Well, and you'll notice that a lot of them, or all of them, take in different parameters. So the reason why we have an impl version that you will be writing, and there's another version that the user calls, is so that some of these details are abstracted away from the user. So a user can see if their binary search tree is empty without knowing that our impl function is seeded with the root node of the container, or the root node of the binary search tree. Additionally, we can see that our check sorting invariant takes in, it's again seeded with the root of the container, and also takes in the less comparator, but the user doesn't need to know these things. They can just call check sorting invariant with and no parameters taken in. But so just note that you will be implementing all the ones that end in impl. And in fact, you won't be touching any of the code above a certain line. I believe it is right here. So line 321, it says, do not change anything in this file above this line. So of course you can examine this thing above, but you won't have to modify anything above line 321 when it comes out of the box. And so we can see all of our impl functions have these assert false. That's what we're going to have to fill with our implementation. So we'll be going through those. One more thing I want to talk about is we also see an iterator for our container. Remember that iterators are wrapper classes for pointers. They're generalized pointers that users can use outside of the class and be able to traverse our container. So they can set iterators equal to the beginning of our tree, move them forward with the ++ operator until the end of our tree, and allows them to traverse the tree without really knowing how it's happening or how our nodes are ordered. Okay. So I'm going to start going through some of these actual functions that you'll be implementing. So starting with empty, this is going to return true if the tree rooted at node is empty. In other words, it returns true if there are no nodes in the tree. So just think about, what does this mean that node should equal if the tree were to be empty? Next, going on to size impl, this is supposed to return the size of the tree rooted at node, which is the total number of nodes in the tree. The size of the empty tree is 0. So again, I would think about, what is the simplest case? What does a tree look like if it has no nodes? What should node be equal to if there are no nodes? How will I know also that I cannot recurse further? What is my definition of a leaf node, and knowing that I've reached the end point of one of my branches of my tree? And then in order to add up all the nodes to get the total size, think about what you should be doing if you do not meet your base case. And so you just have to make sure that you account for every node in the tree, should be doing some sort of operation as you recurse. Okay. Height is different than size. Size wanted us to count all of the nodes. Height wants us to find the maximum longest path in the tree. So you need to be doing some sort of comparison. You can't just add together every time you diverge into another node, because you're only trying to find the single longest path. So you should be doing some sort of comparison to ensure that you return the longest path in the tree. Okay. size and height, done. So copy nodes impl, this is part of our implementation for the copy constructor and the assignment operator, both of which are the big part of the big three. So we need to be making a deep copy. What does this mean? We want to be allocating new nodes on the heap that have the same datum and the same structure as the tree rooted at node. So you should be using the new keyword because you're allocating dynamic memory. Also, we need to return a pointer to the root of the new tree. So I know this can be tricky to think about, how am I going to copy over an entire tree from a given one? But start small. What if I have no nodes? What if I have a single node? How would you copy a single node? How would you initialize it? And what would its left and right children be? And then think about if I have a node and a child that are dynamically allocated, or a node and one left child rooted at the tree that's given to me. How would I connect them together? Because you have to think that I need to still be relating them. I can't just create dynamic nodes. I also have to say I'm creating a parent node whose left child happens to be another node. So just remember to be linking them together, creating new dynamic memory. It's going to have the exact same datum and structure as the tree rooted at node given to us. Okay. So destroy nodes impl, that's going to be in our destructor for the big three. We have to clear out the entire tree by deleting every node. You can think about if I had a node, a parent node with two children, if I delete the parent node, I've now lost my link to my two children. So I can't just start by deleting at the top, because then I have no path to follow down. So ask yourself, how would I find the other nodes? Where should I start deleting? And then how will I sort of trickle back to delete all of them? Okay. Find, I'm going to make a drawing for this one, for find impl. Okay, so dealing with find impl, this is going to return true if the query we're looking for was found in some node in the tree. So we want to take advantage of the fact that the tree is sorted. So we don't need to look at every node, given that we have a properly sorted tree. So we can think about there's three kind of case scenarios that we can run into. I guess we also have a four. Okay. So we can start with case one. So let's say we're looking for the query equal to 7. And right now we see a 3. So 3 is less than 7. If I'm looking for something greater than 3, will I ever find it in the left subtree? No, I won't find it because everything in the left subtree is less than 3. So I'm going to look right. My decision that I make is to look right. Or in other words, I'm going to recurse right. Okay, in the case where I find a node equal to my query, 7 equal to 7, well, that's great. Then I found my query. So what should I return? Remember that this find impl is going to be a, what does the return type be? What does it be? It's returning an address of a node. So if I find it, what should I return? Okay, otherwise, if I find 7, a number greater than 7, 9 is greater than 7, will it ever exist in the right subtree where everything is greater than 9? No, it will not. So I need to look left or recurse to the left to keep looking. And if I hit a null pointer ever, that means I haven't yet found it. So what should I return? I didn't find the query. Okay. now we're going to move on to insert impl. So this is a similar vibe to find, but it's a little bit different. So if we're trying to insert the item 9, will I ever see a 9 itself? Will I ever get a node datum equal to the thing we're trying to insert? And the answer is no. Because remember, our tree does not support duplicates. Okay, so there's 3 case scenarios that we could run into though, and that's the case of less than, greater than, and a null pointer. So where 7 is less than 9, would we ever want to insert a 9 to the left of 7? Well, everything in the left subtree should be less than, and 9 is not less than 7. So no, we would never want to insert into the left subtree. So we have to look right. Or again, recurse right. If we see an 11, will we ever insert a 9 to the right of 11? No, because 9 is not greater than 11. 9 is less than 11. So we're going to look left. Recurse left. And if we see a null pointer, what does that mean? Well, the important part to remember is that the end goal of this function is to insert. So if I finally reached a place in my tree where I'm not looking at a node, then yes, I want to insert here. And remember that our nodes are dynamically allocated, so we should be creating a node with new, and we should be ensuring that it's linked to the tree properly. So if I end up inserting a node right here, I need to make sure that it has the link that the parent is saying, yes, this is my right child node. Okay. Another important thing to remember, I think, for this insert function is that it's not necessarily the most efficient solution. For example, if we have a tree that contains the node 1, and then we want to insert a 2, well, it's going to insert a 2 to the right because 2 is greater than 1. Let's say we want to insert a 3. Well, it's going to insert it to the right because 3 is greater than 1 and 2. And if we insert a 4, it's going to go here. You can see that this is a very stick-like tree. It's not branchy. And the whole point of binary search trees being efficient is the fact that they branch right and left and they're balanced so that we can cut the search size down and make decisions to go less than and greater than every time. So our solution is not necessarily the most efficient tree, but that's something you'll learn in later courses on how to make your tree maintain balance. But that's not something you have to worry about with this project. Okay, so we've gone over insert impl. Min and max are pretty straightforward functions. So just ask yourself, if I want to find the smallest element where it lives, I'm either going to have to look as far in one direction as possible or as far in the other direction as possible. And my only 2 possibilities are looking right and left. So do I go as far as possible to the right to get the minimum, or do I go as far as possible to the left to get the minimum? And sort of the inverse of that for finding the maximum. The next one that we're going to talk about is the check sorting invariant. And I see this function go wrong or misinterpreted quite a lot. So we're going to also go back to the drawing for that one and hopefully clear up some misconceptions with this function. Okay, so we're going to talk about check sorting invariant specifically. We know that for our tree to be sorted, we want the left side of our, or the left subtree to be less than the root and everything in the right subtree to be greater than the root. So what I see a lot of people doing is, and I'm going to write this in sort of a pseudocode, is to say like, okay, I need to make sure that my, oh, I lost my thing, left child's datum is less than my root datum. If this is not the case, then I know that it's not sorted properly. And then I also want to make sure that my root is less than my right arrow datum. And if that's not the case, then I know I can return false. So it's not sorted properly. And people think like, okay, if I just traverse down my tree and make sure that the left child is less than and the right child is greater than, then I have a sorted tree. And that is a good start to this function, but let's just, if we extend our tree a little bit more. So let's say I have here, okay, and let's like imagine walking through that code. So I say, okay, my root currently is this 5, and I see my 3 is less than, so that's good. My 10 is greater than, that's good. I'm going to traverse down into, like if I look at my 10, it doesn't have any children, so it's all good. And then it'll hit the base case. And then if I look at my 3, 1 is less than 3, and 7 is greater than 3, so we're all good, right? But is this tree sorted properly? We'll see that no, this 7 is greater than 5. So that's not right. So by just checking the left child and the right child, I haven't actually ensured that the sorting invariant is followed, because the sorting invariant is not that the left child must be less than and the right child must be greater than, but it's that the entire left subtree must be less than the root, and my entire right subtree must be greater than the root. So it is not enough alone to just be looking at the left and right children. I need to look at a certain property of the subtree to ensure that the entire thing is less than the root. So I want you to look through your functions and see, is there a function for BST that returns some property that would ensure an entire tree is less than a certain value? So that's kind of a long question, but there should be something you can utilize that you've already implemented that by checking that sort of property of the tree, that ensures, yes, my entire left subtree is less than the root. So take some time to think about that, but that's check sorting invariant. Don't get it messed up that you can only check the left and the right child. Make sure that the entire left subtree is less than and the entire right subtree is greater than. And the next one we're going to talk about is the tree traversals. So the next two ones we have are traverse in order impl and traverse pre-order impl. These are simpler functions than you think. There's only 3 possible actions that you can have, which is the printing, and then traversing right and traversing left. So all you have to do is manipulate the order of these to be in order and pre-order. And I recommend, I think in lecture we go over this directly, but also if you're interested, I would click on those links to refresh on what in order and pre-order looks like, and then try on paper tracing through an example of a tree printed in order and see, do you go left first, right first, or print first for the tree so that it's printed in order? And that should give you your answer for how you're going to write that implementation. The next one that we're going to look at, or the next one and the last one that we're going to be going over is the min greater than impl, which is this kind of dreaded function, but don't worry, we're going to go through it very in depth, hopefully like break down every possible case scenario, and then we're going to even write some pseudocode to really help you break down this function. So I will be right back with that. So we're gonna finish up talking about min greater than. So min greater than in itself, it just seems like, what does that even mean that I'm supposed to be finding? But we're looking for the smallest value in the tree that is still greater than the val that is given as a parameter. So for instance, if we're looking for the min greater than 6, so val is equal to 6, and we have this tree rooted here at 12, there are quite a few values that are greater than 6. And I'm just going to circle them all. So there are more, in this case, there's more than one node in the tree that is greater than 6. But only one of them is the min greater than 6, which is the 7 node. So for this example, the min greater than 6 is 7. And we're going to break down all the different case scenarios that we can run into. So looking for the min greater than. If I see a 5, which 5 is less, and again, we're dealing with our val equal to 6. Looking for the min greater than. If I see a 5, 5 is less than 6. Will a min greater than ever exist in the left subtree? The answer is no, because everything is less than 5 in the left subtree. So I need to recurse right to keep looking for a potential min greater than. If I see something equal to it, which this is possible because again, we're not inserting, we're searching, we could find something equal, 6 equals 6. Will I find anything greater than 6 in the left subtree? No, I won't. So I need to look to the right. Okay, so those are pretty simple. And also, if I see null pointer, that either means I was given the empty tree or I recursed all the way down and I never found anything. So did not find anything greater than val, in which I would look to the RME and see what I'm supposed to return. Okay, case 3, this is where it's a little bit more interesting and where we actually have to do some work, because now we've found something finally that is greater than the val we're looking for. 12 is greater than 6. So this, the question we need to ask ourselves now is it the minimum value greater than in our tree? And the answer to that is maybe. So when we see something greater than the val we're looking for, we have a potential solution. Will we ever find anything better in the right subtree? In the right subtree where everything is greater than, will we find something better? The answer is no, we won't find anything better in the right subtree because everything is greater than 12. We're looking for the minimum greater than. So we need to look left, potentially, to see if there's something better. So we need to check the left subtree to ensure there's nothing better. Okay, but we still want to save that 12 as a potential solution because it could be the min greater than, we're just not sure. So how do we do this sort of check in the left subtree? This can be very tricky to think about. How do I, ensure that there is nothing better? Like sometimes it can be difficult to not just keep recursing, but luckily we've handled every single case that we can run into. So all we need to do is recurse into the left subtree with the framework that we've set up, and we need to just save that recursive call. So we can do this. Node star, and I'm going to call this left check. So I'm saving the recursive call, and I'm going to make a call to min greater than. But what node am I calling it on? Remember that node currently points to this 12. What would I call it on? Well, I'm going to call it on the left subtree. So node arrow left. And then I believe the next thing is the val will stay the same. And the comparator less will stay the same too. Okay, so I've just made a call into the left subtree, and I've saved it into this node pointer called left check, which is awesome. Because now I can make a decision based on what this call to min greater than returns. So there's two possibilities for what it could return. Either it's going to, well, think about it. What are the possibilities of this function? There's only two sort of categories we could have. So one of them is a pointer, a valid node pointer, or a null pointer. And what do those mean? What does that mean? Well, if I get a null pointer returned for my left check, that means I didn't find anything better. Nothing better in the left. But if I get some node star, that means I did find something that is still greater than the val I'm looking at. Or is still greater than 6, but less than 12. So this means I found something better, something smaller that's still greater than val. So something greater than val, which in this case is 6, but also less than 12, the current node I'm looking at. Okay, I hope this makes sense. So those are the two things that left check can evaluate to after it's returned from its recursive call to min greater than into the left subtree. So now we just need to think about what do we do with this information. And remember that node, we have 12, node points to the current 12, and then left check points to potentially somewhere in the left subtree or a null pointer. Okay, so in case scenario 1, where I find something better, if I found something better that's less than 12 but still greater than val, then I would want to return it. So I would want to return left check. Oops. But in case scenario 2, where I get a null pointer, I did not find anything better, then I want to return what? What would I want to return? The current thing that I have saved, which is node, because that's my potential solution, or in this case, the one equal to 12. So with following these 4 case scenarios, in the special case of 3, where I need to double check that there isn't anything better in the left subtree, this will account for all the different branches that you could potentially go down. And it can be really, really hard to just think that by having this check that it will do the recursion properly, even if there are better and better solutions nested in the left check, but it does work. And so I encourage you to try tracing through a problem where it would have to do this sort of left check twice and affirm for yourself that the recursive leap of faith does work. We're going to look at some pseudocode of this too, and then that'll be the last thing we do in this video. Okay, so let's just actually kind of sketch out an outline of what this function would look like. It's not going to be necessarily syntactically correct, but we're just going to be writing pseudocode. So let's think about this. Again, we have our different case scenarios. So let's say if I hit a null pointer or an empty tree, I'm going to want to return, so I'm trying to think of how in depth I want to go with this. We know that that means we did not find it. So I'm going to say we did not find anything greater than val. I'm going to leave it at that for you guys. Okay, else if we find a node datum that is less than val, where do we want to look again? We want to recurse to the right. Okay. Else, if we find the val, or sorry, node datum is equal to the val, again, we still want to recurse to the right. You could probably clump some of these cases together, but I'm just trying to write it out as explicitly as possible, break this down. Okay. Otherwise, if we haven't found something, we know that it's not a null pointer, so we know it must be a node. If it's not less than or equal to, and really these could be clumped together into one case because they have the same effect that they're supposed to do, then we know otherwise we have found a val, a node datum that is greater than val, so a potential solution. Okay. So remember, we need to do our left check. Node star left check equals my recursive call, min greater than. I want to recurse into the left subtree because nothing greater than, nothing less than this is going to be in the right subtree. And we're looking for something that is smaller than the current node we're looking at, but still greater than val. And val and less are staying the same. If the left check is a null pointer, or maybe if yeah, something of that nature. Again, up to you for how you exactly want to structure this nicely. But if the left check is a null pointer, then we know that we didn't find anything better. We did not find anything better in the left subtree. So we're going to return the node that we're currently at. Otherwise, we did find something better because left check is equal to some node address, some points to some node. So we're going to return the left check. Okay, which is just the address of a different node, one that is better than the one we're currently looking at. Hello again, guys. I just have two clarifications to make about my min greater than impl pseudocode that I wrote previously. So this call right here should be a recursive call to min greater than impl. So that was a mistake. It should have the impl at the end. Another thing is, you guys will not be using the less than sign to compare datums for nodes. You will be using the less comparator that is taken in as a parameter. So it would look something like this. Taking in both of those datums as parameters to the less than comparator. And if you're wondering how would I encompass node datum being less than or equal to in by only using the less comparator, we could write something like this. So we've taken the inverse and then used not in front of it. So if val is not less than node datum, in other words, val must be greater than or equal to if it is not less than. So that's what you can use to encompass both of those cases and use the less than comparator. So it would replace those two statements. Okay, that's everything, guys. Good luck working on project 5, and I hope you have a good Thanksgiving break